Okay, a ball rolls down a ramp and it achieves some final velocity VF, and we assume uniform acceleration down this ramp. So it takes some delta t to achieve its final velocity from rest. And during this time, the average velocity is VF plus V naught over 2. Since V naught is 0, that average velocity is just final velocity divided by 2. Now, we don't actually have to know all that, but it helps understand the situation. Now, to achieve velocity VF over 2, which is the average velocity, takes half as long. Okay, so the average velocity occurs halfway through the time interval. And I see a way I can clarify that a little, so I'm going to pause here. So now we want to know how long it takes to achieve the average velocity, okay, which is half the final velocity. So the ball goes from 0 to final velocity. You would tend to think that the average velocity occur halfway between here and here, but it's not going to be the case. But it does take half as long to get that average velocity. So we're achieving a velocity v, which is equal to the average velocity, which is of course half the final velocity. Okay, and that's only going to take half as long because the acceleration is constant. We're picking up velocity at a constant rate with respect to time. So first we pick up half the final velocity, and then we pick up the other half. It takes the same time. So that the time to get to half the final velocity is half the time it takes to get to the final velocity. So if delta t is the time it takes to get to velocity VF at the end of the ramp, then the time interval for achieving the average velocity, which is half the final velocity, is going to be half as great. So what's going to happen, and hopefully we can maybe see it already, is that we're moving at, well, we're achieving half the average velocity at the end, so that the average velocity for that time interval, from velocity 0 to velocity the average, is going to be only half as great as before. So let's see if we can get that straight. Okay, we're going to be accelerating for half the time, and we're going to only achieve half the average velocity. Why? Because in this interval between release and achieving the average velocity, we achieve only half of the final velocity, meaning our average velocity for this shorter interval is going to be half of the average velocity for the longer interval. Now we can say that from rest to v equals average velocity, which is VF over 2, our average velocity is going to be, well, we start at 0 and we're achieving the average velocity V bar, the average velocity of the ball if it went the whole length of the ramp, and our average velocity is then going to be equal to the average velocity of the whole ramp divided by 2. Now there are too many average velocities here, so that might be a little bit hard to see. There are ways to write this down with more complicated notation, but they probably would tend to confuse the issue more than they'd help. So the bottom line is that we're going to have half of the average velocity that occurs on the entire ramp. The ball then travels at half the average velocity for half as long, so it's going to travel half of half, or 1/4 of the distance, 1/4 as far, which would be, of course, 1/4 of the 16 length units of the ramp, or 4 length units. Another way of saying it, traveling at V bar for delta t, we travel 16 units, so that V bar delta t is 16 length units. Traveling at half V bar, which is what we're going to travel for the interval where we only achieve V bar as the final velocity, for half the time interval, which is how long it takes us to achieve half the final velocity, we travel 1/2 V bar times 1/2 delta t, or 1/4 V bar delta t, 1/4 of our 16 length units, or 4 length units. Now this is a tricky problem to reason out, but and it's one that I expect to be one of the harder problems on the test. But there's some reasoning that might be helpful. I could also draw pictures. and I might do that on a subsequent video. We'll see.